Today's episode is called When One Case Enough Isn't Enough, Object-Centric Event Logs for Multi-Agent Systems. So let's look here. This is a multi-agent run. So you have a supervisor that's firing one delegate event, and that single event touches 4 things at once. So the supervisor here is actually being touched itself by the delegate run. And 3 tasks are being executed here. So you have one event, many objects. That is the normal shape of agent work. Also, if you want to see how the run of an agent looks like, you can check earlier episodes from the series. We are talking how it looks like a tree. So they are embedded. Everyone is embedded in. So now let's try to mine it the classical way. So we have every tool we have used until now needs a flat table. What does one flat table mean? Is you have one row per event, filed under one case column. So you have to answer a question you should not have to answer: which column is the case? And here we have a problem, because every answer of which column we want to use will cost you. Why is that? If you make the task the case, if the task is our case, then the shared delegate here, as these 3, like this relationship with delegate, has to be copied in all 3 tasks. So one real event becomes 3. If you make the run the case, and 3 unrelated tasks get poured into a single lane. So we have to make a choice here. And that is the whole problem in one line. You have one case ID cannot describe a many-to-many world. Whichever column you pick, you lose something. And the next 2 parts will talk about the exact ways you might lose data. Now, I actually had the video where I was explaining what is convergence, divergence. I will explain it in the context of agentic AI. So this is the first kind of failure. If we flatten, depending on our task, and we make the task our case, then each task becomes its own case. So, which sounds reasonable. The problem is that the delegate event, this one, related to all these 3 tasks, becomes duplicated. It shows up in a row, as you can see, at the same time, and it appears 3 times. And if you build a DFG from here, your delegate count is inflated. So every downstream could be wrong. This is what we call convergence. I explained already in a previous video how the meaning of convergence, but it's all right. And it was defined in 2019. I can explain it again. And in the case of agents, it happens if we go with classical process mining. This is what's going to happen, and it's really problematic. So on the other side, if you flatten on the run, you have 2 parallel workers that land in one lane, and they are interleaved with time, of course. So the miner does the only thing that it can here. It reads that lane, left to right, and assumes that each event is being followed by the other, which is not what's really happening for us. It's giving us, in a way, a neat sequence, which is not the reality of how the span of an agent actually works. So the interleaving is an accident of timing, because some tasks may take a little bit more time than the others. It's not causality. And this is what gets you your phantom DFG. So this is what we call divergence. It's unrelated instances interleaving inside one case, manufacturing an order that was never there. The canonical example, for example, an order with 10 items, and all 10 items pick and ship events tangled together in single case order. So why all of this is actually dangerous in the age of AI? If you use these functions, let's say you're using Cloud Code and you just call these functions from PM4Py, and you think, okay, this is nice. I have my flattening, you pick your object type, and it hands you a data frame. You're happy with it, and you mine it. You get the Petri net. You don't get an error anywhere. So the output that you get is a perfectly valid schema that's coming from your classical log. And it mines into a clean looking model. So, and that's not what you should do as an engineer. You should always check for these, for divergence, because they are mutations of reality. So a log that crashes, you can actually fix. A log that lies quietly and mines in a beautiful way and that you ship can create big problems later on. So there is actually a solution, especially with object-centric event logs here, which is that you have these tables. Please check my videos about OCAL 2.0, where I'm explaining exactly how these tables work, the attributes are working. All of these are important information. And with all of this information of relationships, please, again, check if you don't understand what I'm talking about, especially when it comes to OCAL, please check that previous video. What you would do in practice is that you would flatten on demand. What do I mean by that? So a different case notion will be, there will be a different flattening depending on a different case notion. So for example, you want counts per task, you flatten on task. You want the flow of a run, you flatten on a run. The case notion becomes a property of the query you're asking. It's not a decision that's frozen in time. So this transition from classical process mining to process mining is very important. So all of this is very important is because multi-agent, 32% of multi-agent failures are on the level of inter-agent misalignment. For example, it's the interactions, the coordination, the handoffs, the message flow. This is coming from the 2025 paper of Must. And what the flattening destroys is actually precisely the interaction structure. It's the relations between the agents, the tasks, the messages, because you're flattening on every object. It's either the run, the task. These are all questions you need to proactively make a choice for. And one thing I wanted to mention is that all of this convergence, divergence, this explanation is from a 2019 paper from Van der Aalst, and it's an application, and the application of them to multi-agent LLM traces is an idea from this series synthesis. It's not prior literature. Hopefully I will find the chance to write a paper about this, a paper that is rigorous enough, of course. So two honest notes here. There is an open agent traces in OCL 2.0 generator. What it does is that you have 7 object types and it generates synthetic data. It's not a converter. A converter is really hard to build and it's a very case-by-case situation. You can't build a converter that will solve all your problems. And one thing I wanted to say is that one handoff equals one event on many objects. So this is an OCAL modeling choice. This is coming from the E2O table. In row traces, those are different, those are often separate nested spans. So you need to build a relationship there too. So finally, to recap, here is some PM4 pseudocode. You have the different functions. I really don't need to read you the different functions because you can find the documentation of PM4 online. And yeah, it would be a loss of time if I did that. You just, generally, if you're a developer, engineer, or researcher, you just need to understand the concepts. And then when you can communicate all of these concepts, you can have an exchange with your coding agent and it can do the changes for you. So of course here I can tell you that this is for the O2O table, this is for the flattening. All of that information is nice, but you can learn it on your own. And to recap, here you have 3 things to keep in mind. You have picking one case is a bad idea because you're creating these problems. Also, if you pick one case, you're not considering a part of the data, which would be stupid. Then we have shown how OCL avoids the choice by keeping every. And finally, we have spoken about how you flatten on demand per question. One tip: keep the O2O, the E2O tables, your OCL structure, and only flatten in the end. The last thing to do, maybe a smart way to do this is to keep a centralized database, and then per case, how I described earlier, you would flatten.